Yes. Again, warm welcome, Rasika. And it's always our great pleasure that our alumni are working very, very at high position in different sectors. And when we hear as a from our alumni, it's really we feel really good. So from that point of view, also, initially, I thank you for joining for this FDP as a resource person. So I request you to start the session.
Okay, yeah. Let me share my screen. So is everybody able to see my screen? Okay. So first of all, I would like to take this opportunity to thank Professor Dr. Maitre ma'am for giving me this opportunity to talk with all of you and share my industrial experiences. And thank you to VIT professors and the department for giving me this opportunity and this making this platform, online platform available. So yeah, let's get started. So today I'll be talking about VLSI test strategies for memristor circuits. So I think Dr. Maitre ma'am has already given introduction about me, but little bit I can give you some background. I'm currently working as an engineering manager at Altera Corporation. So Altera is one of the leading industries in FPGA manufacturing and also SOCs. So before Altera, I was working for about 11 years at Intel Corporation as a product development engineer. So most of my work and my expertise has been on VLSI testing for semiconductor devices, a lot of memory and configuration testing, and post-silicon and yield improvement. So this is something I would like to share today with all of you, some background on VLSI, on test, on manufacturing testing, and how we can improve the yield of our silicon devices. And yeah, about my education, I completed my PhD from Portland State while working at Intel, and also my master's from Wisconsin-Madison. And I was a student just like you all. I graduated in 2012 from a VIT, Instrumentation and Control batch. So yeah, from VIT classroom to Intel Altera Fab, it has been like a long engineering journey, and I would love to share some of my experiences and also get any questions, or if you want to know something more about semiconductors, we'll try to have more of an interactive session. Okay. So we'll divide the presentation into two parts today. So the first part, we are going to discuss about VLSI test strategies. I'm going to introduce you to the VLSI life cycle. We are going to talk about manufacturing testing, why it is so important. And we'll also see what different tests are being covered under manufacturing. We'll talk about defects and faults, and the fault modeling in this manufacturing testing, and how we are coming up with efficient test during our manufacturing process. So the goal here is to deliver a high quality silicon, right, to our customers, and coming up with the right strategy. We'll talk about what equipment is being used in these different semiconductor fabs, such as Intel, Samsung, TSMC, right? You may have heard of these companies. We'll see what instruments they use and what type of debug strategies. And the second part of the presentation, we'll see how we can apply these test strategies to different type of memristor circuits. Okay, so we learn about a new memristor device. It's a nanotechnology. We'll see how we can apply these fault detection principles to memristor devices. Okay, so if there are any questions, feel free to interrupt me, like any clarifying questions, anything you have. And also we'll have a detailed Q&A session towards the end of the presentation too. Okay. So have any of you seen this VLSI realization process before, like the life cycle? Are you folks familiar with this? Okay. So our goal is basically to deliver silicon, right, to our customers. So our customer may have different set of applications like 5G, AI. There will be different customer needs, and based on that, we have to design our chips, right, our customer products. So we determine the requirements, we write the specifications, and we write the design in register transfer level logic, such as Verilog or VHDL, right? We synthesize the design and make sure all the components of the design are being implemented correctly as part of the verification. So all of these steps, they form as part of our design process. So when we do the design, we also have to make sure that all the components are working correctly. So we also need to have a design for test circuitry, which is going to be part of this same design architecture, and this is going to be part of our test development. So once the design is ready for fabrication, once we know that all the steps are working correctly from synthesis to verification to physical design, we send these chips to fabrication units to Intel or foundry labs like Samsung, and we fabricate or create those metal layers or metal lines and actually have a silicon wafer, which we have to manufacturing testing on that. So the manufacturing testing will help us tell, right, if there is any defective part, if there is any good part. So it can tell us whether there are passing or failing units, and we will ship the high quality chips or those silicon units to our customer. So that is our entire VLSI life cycle that we are talking about here. So in these semiconductor industries, each of these groups, they are working on different parts of this life cycle. You'll see someone doing design, you'll see someone doing verification, somebody doing test development. But for today's talk, we are going to focus more on the manufacturing piece here. We are going to talk about manufacturing testing, what are different test methodologies that are we are going to use, what skill set we are looking for. So this is what today I'll be spending more time on. So let's try to understand few concepts before we go into manufacturing test, right? So we talked about verification that happens during silicon design process. So verification is basically ensuring your implementation of all your design logic components, they are matching the design intent. And manufacturing is happening when the design has already been fabricated and we are making sure the implementation is free from any defects. So what type of defects are these? So these defects can happen during process, when you are processing the silicon, during nanoscale fabrication, during assembly, packaging. There are different stages of manufacturing. So this manufacturing process or this test becomes very difficult when your design is not fully validated. You want to make sure your design has correct timing closure done, no violations. You have to make sure the design is passing all your timing checks, physical layout checks. So all these are things that are have to be covered in the verification step. So verification is difficult when manufacturing is not robust, and manufacturing is difficult when design is not fully validated. So these are two important steps. So first step happens in the silicon stage when you are in the design stage, and manufacturing step happens in post silicon stage when your design is ready and fabricated. So these are the two important steps we should keep in mind. So why is manufacturing testing so important? So everybody is familiar with Moore's law here, right? We know Moore's law. So Moore's law is basically your integrated circuit count, right? Which is doubling every year, right? Your number of integrated circuits, your transistors are basically increasing on these chipsets. Your feature size is reducing, your size of your chip is going low. So all your mobile phones or laptops that you're using, they have such tiny, tiny chipsets, right? So we have come all the way from 45 nanometer feature size, which was 4 or 5 years back, to now we are at 3 nanometer. So these leading semiconductor manufacturers such as TSMC, Samsung, they are delivering feature sizes from 345 to now 3 nanometers. So you can imagine such a tiny chip that is coming from our fab. And the operating frequencies also, they have increased a lot. Like we were at what few megahertz before, or 1,000 megahertz, and now we are at few gigahertz, right? So the frequency of operation has also increased. So your probability of defects will also increase because of this scaling, right? So the testing that we are doing is going to ensure that we have fault-free integrated circuits. You want to make sure there is reliability. All these phones that you're using, laptops that you're using, you want to ensure they work for the next 5 to 10 years, right? So you want to improve the reliability of the product and get good customer shipments, right? You want to make sure all your customers, which are the consumers of the semiconductor yield, have also good defect-free chips. And when you have an efficient production test, you're going to shorten the time to market by diagnosing these defective IC quickly, right? And the main goal is also to reduce the test cost. So all these devices, they are going to go into different applications. They will go on printed circuit boards, they will have system level testing, field level testing, and this is going to like increase your test cost if you delay your manufacturing testing in each of these steps. So it's better to do the testing at the device level itself than wait for it to go into the system and then do the testing, because testing is going to be expensive, because that test equipment or the processes are going to be even more complex, right, as your size of your system grows or your application grows. So the goal is to reduce the test cost. So what is really this manufacturing test, right? So the goal is mainly to determine whether our hardware is functioning as expected, right? It's working correctly, or whether it's defective. So we want to catch these defects during our fabrication. So when we say fabrication, we have a lot of processes involved. We have lithography, we have masking, we are actually creating, right, the semiconductor layers and metal layers. And then once we have our wafer, we are going to do assembly, packaging, we are going to have different manufacturing stages. So at each step, there can be a possibility of a defect. So what are these defects? So they can be either hard defects or they can be soft defects. So hard defects are something that fails at all the test condition, right? It could be at all the voltages, at all temperatures, frequencies, or it could be like a soft defect, right? Something like a marginality at the circuit level, or something, a timing issue happening in your flop or register. So in this way, in this type of defect, maybe you might see the part partially working, right? You might see silicon passing at low frequency, passing at failing at high frequency, or passing at cold temp, failing at hot temp. So you'll see some sensitivity to temperature or frequency. So these type of defects are soft defects. So let's look at some examples so that you can understand this better. So hard defects are something which you can think of physically. It can be like a short to ground or VCC. So they can give rise to stuck-at defects, where the metal line or your metal layer is basically shorted, right? You can see in this figure here. So here we can see, let me just turn on the pointer. Like there is a short happening here, right, on the middle metal layers. So this is one of the stuck-at defect. You can also have a bridge type of defect, where there are two metal lines running in parallel and there is a short happening between the two. Or it can be a soft defect, like I said, like a timing issue, something happening in the speed path, like a transition delay, right? Your data is not propagating, your data is propagating slowly from your input to output, or a resistive short or open. So there will be different type of soft defects or hard defects happening, right? So these defects are numerous, right? They can happen at any place on any silicon, and they're very difficult to analyze. You cannot physically go and check every metal layer. So we need a efficient fault model that can find a good set of test vectors, and we can maximize your test coverage, right? So this fault model, what it will do is basically apply the right input and outputs to make sure that you can detect that fault. So you will see in literature, there are many fault models that have been defined, like single stuck-at fault models, transistor open and short, memory faults, analog, delay. So there are multiple examples. But for today's lecture and for today's scope, we'll stick to single stuck-at fault model. So we'll talk about single stuck-at faults and how we can detect them. So let's look at an example of a single stuck-at fault. So physically we understood, right, what single stuck-at is. The metal layer can be a short or to VCC or ground. But how do we do a logical representation, right, at the gate level? So you can see here, this is a small circuit, right, with NAND gates. And here we have a stuck at zero node at H. So basically, that means that this node is stuck at zero. That means it cannot propagate any ones, but only can propagate zeros. So when you apply this test vector, like when you apply a 1 and 0 to A and B node, you can see a good circuit value and a faulty circuit value. So in presence of this stuck at zero fault, your faulty circuit value is 0. But in presence of no fault, like say this was a normal regular line that is going to the input, your good circuit value would have been a 1. So basically, by applying this test vector, you are able to sense or sensitize this fault and basically detect it by comparing this good circuit and faulty circuit value. So you're able to detect the fault at the output, right? So this fault or this process of applying test vector and also detecting the fault is called as fault detection. So this stuck at fault can happen anywhere, right? It can happen at the input or output of the gate. It can be stuck at zero, as in this example, but it can also be stuck at one. But we want to see how we can compare these two, good circuit and faulty circuit, to detect the fault. So that is the concept here that we will keep applying for test generation. So test generation is basically the test pattern, or in the previous example, you saw how we applied, right? The 1 and 0 as our test vector so that our output can be analyzed for the correct response. So that is a test. And the process of detecting those faults by applying the test is going to be defined by fault coverage. So fault coverage is basically the total number of detected faults over the total number of faults. So it's going to be, in that particular example, we were able to detect the fault, right, at node H. So fault coverage is something we cannot achieve 100%, right? There will be some corner cases, there will be always some faults that are going to be undetectable, right? So in industry, in semiconductor, we always try to target like 95 to 96% of our fault coverage. And it will be for all these stuck at or at speed or other metrics, right? We'll cover a lot of these faults in this process. But our goal is to ensure that every part of the chip, right? All our memories, our processors, our CPUs, DSPs, everything has to be covered for faults, right? We need to have that specific test pattern that targets every IP on the chip. And this testing happens at different parts of your manufacturing. It will happen during fabrication, during assembly, packaging. So we have a very high level, like this is a high level flow, but it's very detailed at every step. Like at every step, you will see we have multiple manufacturing steps happening here. So we have the wafer coming from the fab. We test that to see how many units are passing or failing. Then we do a assembly to check for defects. So only the good parts are screened out and going to assembly, packaging. We have reliability stress testing at high voltages and high temperatures to screen out any reliability related defects. And then we do hot and cold temperatures and testing, fusing, and also bench level or system level testing. And finally, the good set of units are being shipped to our customer. So our goal is basically to screen out all of these units at the initial phases of manufacturing, because it was going to get very expensive. Like for a package unit to test is more expensive than testing a wafer level, right? Because the testing equipment, your test duration is going to increase as your part goes into system level. So that is your high level manufacturing flow. So we looked at the test generation, right? In the previous example, we saw how the test vector is being applied. So goal of a good test is basically to get us good observability and controllability. These two are important things that we need to see when we apply a test vector, right? You could see how the data is propagating from every node, right? On for that NAND gate, which we looked at. But can we really check all these NAND gate inputs and outputs in a real life scenario? Just imagine an integrated circuit with so many transistors and AND gates and NAND gates. It's going to be very difficult, right, to test every node. The test cost will be very expensive and it will be a very exhaustive test. So that's why we need to introduce something called design for testability. So these are basically test architectures which are being defined on our silicon for having efficient test vectors. So good design for testability examples are scan and built-in self-test. So scan is basically you are adding some control elements to your flip-flop. So before scan insertion, you can see this is a normal flip-flop, but after adding some scan elements like scan enable signals, scan in signals, you are able to get visibility into the data, right? You are having some observability here to see what is the data going in. You can see the expected data that is supposed to come from the flop, and you can compare it with the actual response coming from this combinational logic. So it's basically a comparison of expected response versus observed response. So controllability and observability is what we are doing in each of these different design for testability examples. So there is memory built-in self-test and boundary scan. So we'll look at high level how this architecture works. We won't be going into much detail on the theory part, but high level, you need to understand that what we are comparing here, right? So for example, this is your memory cell or a memory BIST. In this example, you are testing a memory cell. So you are having some read column decoder, address decoder, which is going to generate your expected data. And the actual data coming from the memory read write is being compared with this expected data to tell if the memory has a fault or whether memory data is passing or failing. So this all this is happening through hardware, right? We are actually applying this to the circuit under test, which is called cut, and we are applying this data through the tester, which is our automatic test equipment. We apply these patterns through our pin electronics. We get the in the data from the circuit under test and we compare it, right? The expected data versus observed data. And we store these responses and basically determine if the device is passing or failing. So that is the high level testability methodology that we have to apply for all of these DFT architectures. So what is this automated test equipment that we are using? So these testers you can see very commonly used in all of these foundries and all of these semiconductor labs. And they are really very expensive testers, like millions of dollars. So that's why I'm saying test time is very expensive. So what this tester is doing is powering up our packaged parts or our silicon, sending the stimulus and observing the response. So this is the main flow that you need to understand. So we run some softwares on the tester to run our test patterns or these test vectors. And it has a good amount of hardware. It will have a probe head, a probe card. It has a very powerful computer like a digital signal processor computer, and also the software, which is our test program, which we load on the tester. So these some of these common examples of these ATs are from Advantest. We have T2000. We have Intel's HDMT, the high density modular tester, V93K. There are a lot of tester platforms which are being used in industry. So let me show you how actually the tester components look like. So we have printed circuit boards. This is the actual test interface unit in which we actually load our silicon parts. We have a socket to apply our voltages and also our frequencies. And to control our temperatures, we have a hand socket lid, and we have a probe card, right? For any wafer level testing, we have a probe card. So these are some of the components that you will see a lot being used in the tester environment, okay, on the ATEs. So how would the data look like, right, on the ATE? So you want to understand whether the silicon is passing or failing. So one of the representation of data is called SHMU. It's basically a graphical representation to see at what voltages or frequency or different test conditions our data is passing. So for this particular example, you can see we are executing our test pattern from 1 volt to zero point 0.6 volts. So this region is passing green. That means there is no defect and it's passing clean. And this region is failing. That means something, the transistor is breaking down, or it's basically that means that our test has stopped functioning at this voltage. So this is one of the examples. And there are different tools on this ATE tester to see how our silicon is performing. Okay. So that comes towards the end of our first part of our presentation. We looked at VLSI test strategies and how it's being used in an industry and industrial environment. Any questions so far from anyone? Okay. So
So
we will, yeah.
uh, actually, after the having the components on the chip or at the chip level, you are test after that it is tested, no? You are this is the test procedure after that
Yes, after the transistors are fabricated, correct.
fabricated. Okay. So at a time, how many components are tested? Can be tested with the test bench.
Yeah, so we have a lot of big handlers in the lab. You can test at least 100 parts at a time. You can do parallel testing. You can also test one by one, serial testing. There are different functionalities of that automated test equipment. But the goal is to do volume based testing. So usually 100 to 150 parts is something we can run in one go and run different test patterns on that.
Beforehand, the actual design is with you, na? How the components are connected with each other, and what should be the input and what should be the output.
Yes. So at design level, we would already know, like when we code the Verilog or do the synthesis, right? We would already have the design level information. So that design is what we are putting into the physical layout, right, of the chip, into actual metal layers and actually putting it in the VRs and the semiconductor physical structure. And that's what is going to be packaged and sent for further testing.
Yeah, good. Go ahead.
Okay.
Yeah,
Okay, so now these test strategies, we are going to see how we can apply it to a nanoscale device, which is called Memristor. Okay, so does anybody here know what are memristors? Okay, so we'll talk about a little bit about memristor theory. Okay, we'll discuss what are the benefits of memristor, what are the different applications, how they are being used in crossbar arrays and sneak paths, and we'll also see the different defect models in memristors and how we do a memristor testing, right, in the lab, or how we use the automated equipment for testing these circuits. And we look at some of the test strategies too, right, because these memristors, they will have some of their unique properties which will be coming from these devices. So let's try to understand the need, right, for memristors. Why do we have memristor devices? So with Moore's law, there have been multiple challenges, right? As you may have known, CMOS technology is growing, but there are also challenges with heat dissipation, power problems, because you have so many transistors on one particular chip, right? The transistor count is increasing. Like there are thousands or 10,000s of transistors. You are falling short of a power aware architecture. Your manufacturing costs are also increasing, fabrication costs are increasing because your feature size is going down from 45 to 3 nanometer and below. So Memristor is that one device that can handle some of these limitations. It's a non-volatile device, and we'll also see later what are the different advantages. So it has capability to replace these semiconductor devices as well as create hybrid devices, like have a CMOS memristor device, and it can be used in different applications like RRMs, AI, security image processing. You will see a lot of applications being used for memristors. So what is this memristor? So memristor is nothing but it's a two-terminal passive element where we apply input voltage and we measure the output resistance or output current. So your output resistance, it varies based on the history of input voltages that you're applying to it. That is why it is called as a memory register, because it remembers the voltage that it was applied to it. So this memristor, it is like a fourth fundamental element after resistors, capacitors, and inductors. So the concept of memristance, it was came along, I think, by 1971. So physicist named Leon Chua actually discovered this concept. So basically, resistor, right, is the link between voltage and current. Capacitor is the link between charge and voltage, and inductor is between magnetic flux and current, and memristor is that link between magnetic flux and charge. So we'll see how this link is being formed in the next slides. But some of the advantages of memristors are the non-volatile that I talked about, and it's very low power device. It is compact. It has good data density. It can store multiple bits and very fast switching speeds. Like for a transistor, right? We need the transistors to switch very quickly from on and off. But for memristor, the switching speeds are almost less than 1 nanosecond per operation. So it's very very quick for a memristor application. So it has potential for replacing even flash memories. And right now in the semiconductor industry, we have seen it is already replacing DRAMs and hard drives. It can be used for neural networks, neuromorphic systems. So it's a major component for AI and ML systems as well. So we'll see like high level how this works. So this is all of you are familiar with semiconductor and how this PN junction works, right? The potential barrier. So all of us had studied that in our, I think, undergrad, and also in 11th and 12th, we have learned about PN junction. So memristor operates in the similar way, right? So it has a titanium dioxide thin film sandwiched between two platinum electrodes. So this titanium dioxide thin film is divided into two parts. We have like a non-conductive titanium dioxide and a highly conductive titanium dioxide filled with oxygen vacancies. So when you apply your input voltage, that's when these oxygen deficiencies are going to start moving, right? It's going to create that ionic movement. It will start moving to the opposite layer of the titanium oxide, and that's how it is going to create a potential barrier region here. That boundary is going to cause conductivity in the memristor, and the memristor will start conducting. So similar to how any potential barrier or a PN junction works, right? So it's going to start conducting when you apply the positive voltage, and when you apply a negative voltage, these ions are going to start drifting in the opposite direction. Your output current is start going to reducing and your resistance will start increasing. So now this memristor is behaving like a switch. Based on your application of positive voltage or negative voltage, the current is going to vary, your output current and output resistance. So that is because of these ionic movements of these titanium oxide layers. So this memristor, it behaves like a hysteresis, like it shows a hysteresis loop, as you can see. It's basically on switching loop and off switching loop based on the memristor voltages that you are applying. So in this case, when you apply a positive voltage, memristor will start conducting, these titanium oxides start moving, and your output current will start increasing. But when you apply negative voltage, you will see like these current starts dropping, right? Because your these titanium dioxide start moving in the reverse direction, and your resistance of the device is increasing. So this particular type of graph is a hysteresis loop, like on switching and off switching loop, and it's a unique characteristic of a memristor device. So that's what we looked at, right? We looked at when we apply the positive voltage, that's when we get a low resistance state and a high output current. Or when you apply a negatively biased voltage, that's when you see a high resistance state or a low output current. So the total memristance of the memristor is a function of this R on and R off, your lowest possible resistance and highest possible resistance. And alpha is the ratio of the width of that doped region of the titanium dioxide to the total width of the titanium dioxide or thin film. So similar to what any other semiconductor device uses. So that's the main idea here behind a memristor operation. So we can do read and writing into the memristors. So whatever voltages we are applying to achieve that on and off state, we can represent that in terms of logic levels. So when you are trying to write a 1 into the memristor, what we are really doing is applying a positive voltage to achieve that R on. Or when we are trying to write a logic level 0, we are applying a negative voltage to achieve that R off. So think of it in terms of logical levels, how you'll apply ones and zeros, right, to the memristors. And similarly for read, you have to apply the read in such a way so that you don't disturb the state, right, of the memristor. So we apply like a negative pulse followed immediately by a positive pulse with the same magnitude. So there is no change in the resistance due to this, and we can cause a non-destructive read. So that's how a simple read write operation works for memristors, and we have to use these memristors, right, in different crossbar arrays or memory operations or RRAMs. So all of you may have heard of crossbar array, right? Something for SRAMs or even for transistor arrays. You may have seen these horizontal vertical arrays where we have each memristor or a transition at the intersection of this word line and bit line. So you can see how it looks like in terms of the layout or physical layout, how this crossbar area would look like for a memristor. So you can see we apply voltages at the word lines, these horizontal lines, and you measure the output current from this bit line. And we have these black colored memristor devices at each intersection of this word line and bit line. So now when you apply the voltage and measure the voltage, measure the current from this sensing register, this particular memristor is going to be switched on, right? Because the word line connected to it is switched on, bit line connected to it is switched on. But there are some other memristors which will be sharing the line with the word line. So Rn in this example is sharing the word line with the selected device, but its bit line is off. So this is a half selected device. So Rn and Rm also, it is sharing the bit line, but it does not have any word line selected. So such type of devices are half selected devices, or there could be other memristors which are not connected at all, right, to the word line or bit line, and these are unselected. So what are we really doing, right, with these half selected and unselected? We are forming something called sneak paths. So you may have heard of leakage current paths happening in transistor circuits or any circuit, right? So sneak path is like a similar leakage path or undesired path that you would see in the memristor circuit. So we are seeing here in this example of a 3x3 array. So we have 3 word lines and 3 bit lines. So in this memristor is switched on, right? Because this word line is on, bit line is on. So we can see this current flowing, this blue colored path. But there are some other red colored paths which are running in parallel to this blue colored path, which are unintended. So these are called as sneak paths. So they are going to impact your output current, right? So output current coming from this bit line is going to be a summation of this intended path plus this sneak path. So we will see how we can characterize these sneak paths. So they are actually undesirable paths, but we can use them for our advantage for testing. Okay. So these are some of the terminologies that you all need to know. So we talked about intended current path, the blue colored path, right? So this is nothing but also called as primary current path. And then these red colored paths are sneak paths, which we are seeing here. So the output current is going to be a summation of this blue colored and red colored path, right? Which is primary and sneak path. So our total sneak path is going to be a summation of each of these sneak paths coming from these different memristors. So now let's do some example to understand, right, this sneak path. So now can someone tell me in this example, where is the sneak path? Nobody? So in this we can see, right, there is a red colored sneak path. It is from M3, M1 and M2 memristors. So our actual current was flowing from M4, but we have a parallel path, which is our sneak path in this example. So similarly, for a different example, you can see this is our blue colored intended path, right? And where is our second sneak path now?
From M1, M2, and M4.
Right. So this is our second sneak path, which is flowing from the remaining memristors. So these are parallel paths that are basically that we studied as sneak paths. So now let's understand how we can detect faults using these sneak paths. So we are going to first understand something called test vector in a memristor. So we looked at that array, right? We looked at that 3x3 array. So let's call n as the number of rows or word lines and m as columns or bit lines, right? So n open is basically the number of word lines which we are connecting to the voltage source, and n closed is the n open is the one not selected, and n closed is the one selected. And same thing for m open, the number of bit lines not selected, and m closed is selected. So selected, unselected is nothing but you're connecting to the voltage source or not connecting, or connecting to the current source or not connecting for the word line or the bit line. So here we are defining X as our input switch vector and Y as our output switch vector. So you remember that same example that we had seen, right? For the AND gate, NAND gate, stacked example, we applied the test vector. So 1 and 0 is what we applied at the nodes. So this is that test vector basically that we are applying to this memristor circuit. Okay. So our test vector is basically the input states of the word line combined with the output states of the bit line. So for this same 3 by 3 example, we have 3 word lines, 3 bit lines. We have one word line which is switched on, 2 word lines that are off, 1 bit line is switched on, and 2 bit lines are off. So in this case, the input switch vector is 1 0 0 because one of your word lines is switched on, and output is also 1 0 0 because 1 bit line is selected. So this is how we come up with a test vector for any array. Okay, for any array size, this is for a 3 by 3, but for any n by n array, you can derive the test vector. So let's see how we are looking at the sneak paths, right, for this 3 by 3 array. So this 3 by 3 array, you can see there are 4 possible sneak paths. You can see them highlighted in different colors. So here we apply this test vector 1 0 0 1 0 0. And we have our primary current path and these 4 possible sneak paths, which you can see here highlighted in different colors. So in this example, what we can see that when you apply a test vector, you are able to create a primary current path and a sneak path, like 4 sneak paths. So we'll see how we can use these sneak paths later on for our fault detection. So as part of my research work and also industrial work, I did some analysis on the sneak path to understand, right, when there will be scenarios when there will be no sneak paths. So if there are no word lines or bit lines which are open, like they are, if all of them are connected to the voltage source or current source, you will not have any sneak path, right? Because every path there now is going to be your intended current path. But if there is at least one word line or bit line which is open, right, which is not connected to our voltage or current source, then it's possible to have a sneak path. So right now we looked at 3 memristor long sneak paths, right? You saw the length of that memristor sneak path was 3. But we can get longer than 3 memristor sneak paths if we have different resistance programming, right? If you have a combination of high and low memristor resistance programming, you can create long length sneak paths. So you can have 5 memristor long sneak path or 7 memristor. Using this formula, you can calculate the length of the sneak path for any array size. So for a 3 by 3 array, the longest sneak path we can get is 5 memristors long. So this is what we have derived, like different formulas for different type of circuits, for different array sizes. We can predict what will be the length of the sneak path and how many possible sneak paths we can have. So the goal here is to do understand like why we are creating these sneak paths and why it is important to have a long length sneak path. So you can see in the previous example, if we would have had a long length sneak path, more memristors would have been tested, right? Because that length of that memristor is say 5 memristors. So 5 memristors can be tested at a time. If we have 3 memristors, so 3 memristors will be tested at a time when you apply the test vector. So it's very important that we have a long length sneak path so that we can have better test coverage. So that was about the length. So what about the current, right? We need to understand how current plays an important role for fault detection. So the current here is also dependent on multiple factors. We need to understand what is the resistance programming, the low resistance value, high resistance value, what is the array size that is being used, right? And what is the input voltage that we are applying to the array. So these are the different test conditions that we need to define first for that array. We need to understand the boundary conditions for the different applications. And eventually, you want to have a reference current and the sneak path current as RF, like the output current coming from that crossbar. You will do a comparison of those to provide insights to the crossbar array testing. So the sneak path current, like I mentioned, is a function of the size of the array, the resistance programming, IO switch vectors or our test vectors, and our intended current. So what we do as part of our testing is we take these sneak paths from a Python generated tool. So we can, for any crossbar array, we can tell how many sneak paths are possible, right? What is the length of that sneak path? And we can feed those sneak paths into a spice simulator tool and simulate the current values to get the sneak path current. So that is what is the process for the current analysis. So for the resistance programming, there are different resistance values that have been published in literature. There will be 10k ohms for low resistance, 1 meg for high resistance, which is commonly used. But there are different studies, and different foundries use different type of resistances in this for the array simulations. Okay, so let's try to understand now how we can do the current analysis with respect to resistance programming. So for that same 3 by 3 array example, right, where we applied the input switch vector 001 001. Now say we have all the memristors programmed to high resistance state, which is 1 meg ohm. We have a primary current and we have a sneak path current. But suppose one of the memristor has a fault, right? So say out of all the high memristors, one of them is now a low resistance. So it is say 10k ohms. So now you saw your current changed, right? Your current changed from zero 0.8 microamps to 1.14 microamps. So this was your reference current when everything was fault free. And this was your faulty current when one of the memristors is faulty. So this sneak path difference between the reference current and the new faulty current is going to help you to detect a fault. So the same methodology that we studied, right, where we saw we apply the stimulus, we get the output response, and we compare to see if the device is faulty or fault free. So that's what we are doing here for a memristor device. We are using the resistance programming to define whether there is a fault or not. And the sneak path current comparisons between this reference current and the new faulty current is going to tell you if there is a fault in the system. So this is how we can see how we can do fault detection with this sneak path analysis. So why do we need to do this, right? Why do we need to analyze these currents? Because again, this memristor technology is new, the process is new, the fabrication is nanoscale for fabrication. So you can imagine that it will have a very high density of defects. So again, these memristor sockets will have a very similar fault model like the ones that we looked at, right? It can have defects such as broken metal lines or something metal line is missing. So such things can go wrong, right? There is some noise particle in your fab. So something can create this type of stuck at or bridging or stuck open, stuck short type of faults. So for today's study, we'll primarily focus on stuck at faults, right? Like we'll just focus on stuck at 1 and stuck at 0 for our analysis. So we looked at stuck at LRS fault, which is basically stuck at logic 1. So even when you apply a negative voltage to turn off the memristor, it's not able to because it's stuck at logic 1, similar to what we saw, right, in the NAND gate example. And or it can be a stuck at HRS fault where it is stuck at logic 0 when a positive voltage is applied to the memristor to turn it on. So these are very commonly used fault models in memristor. But there are other fault models as well, like the slow to write, like a transition delay type of fault model where the memristor is taking a very long time, right, to switch to a 1 or switch to a 0. Or it can be like in a deep state of zeros or ones. So there are a lot of fault models that are being studied, and we are trying to apply them on the simulation side and also observing them on the silicon side. But for our study, we'll look at only the stuck at 0 and stuck at 1 for today. So we looked at the fault detection principle, right? I showed you how we can vary the resistance programming to detect the fault. But what are these different fault detection techniques that we can do for memristor? So either we can do like a exhaustive testing where we test one memristor at a time. So this is basically testing one memory element in the increasing or decreasing order, right, of the memory. But this type of testing is very time consuming, right? You will have a high test time, and on the testers, it will be very expensive to apply and test the pattern. So the test cost will also increase. Or you can use sneak paths, right? With sneak paths, you are testing multiple memristors at a time. You saw with that sneak path length of 3 or 5 memristors, you can test multiple memristors, right, at a time, and you can observe if they are faulty or not. So with this method, you can see the test time is reduced. You can detect multiple faults at a time, as well as you can get a high fault coverage. Or you can do hybrid testing where we can use both march and sneak path tests at the same time, and also we can get reduced test time. So there are these different methods that we have explored for memristor fault detection. So let's try to understand, like, high level, what the fault detection methodology is, right? So the detection for a stuck at high resistance fault is basically you will initialize the entire array to a low resistance state. So basically, you will take the memristor circuit and assume, right, there is no fault, right? It is everything is low resistance state. You measure the reference current or the fault free current, and then you start iterating through those IO switch vectors. You start applying your test vectors and try to see what is the output current or the circuit under test current. And you compare this fault free current with the circuit under test current to see if a fault is being detected or not detected. So you have to keep doing this iteration until we can say that there is no fault in the system. So this test vector or the IO switch vector is what is going to determine how many sneak paths are possible, right? Of every combination of the test vector will have different sneak paths, and this I cut is nothing but your output current, which is going to comprise of the sneak path. And the same thing we can do for stuck at low resistance fault, right? For stuck at low resistance fault, also you can initialize first the entire array to a high resistance state, right? And then you will measure the fault free current, iterate through all the word lines, bit lines for the IO switch vectors, and compare the reference current and the circuit under test current to see if there is a low resistance fault. So same methodologies, just the initialization process is going to be reversed. So we can see how we can do the same method even for a 3 by 3 array. Like the same example of fault detection you can apply here. You can see these 4 sneak paths from different colors are going to contribute to the sneak path current. So all these memristors in this word line and bit line are going to be tested. And if the reference current is greater or than the expected current, then you know, right, that there is a stuck at LRS fault or high HRS fault in this programmed HRS program array. So this programming that we are calling low resistance, high resistance is nothing but the on-off switching, right, that we are doing. So we looked at the titanium dioxide, how it switches from on to off to on. So same concept is being applied here for the LRS and HRS, or the low resistance state and high resistance state. So those were 3 memristor long sneak paths. But like I mentioned, we can have a long length sneak path also, like a 5 memristor long sneak path. So you can see in this example, M1B, M3B, M3C, M2C, and M2A. This is a 5 memristor long sneak path. And this 5 memristor long sneak path was possible because we have different sets of programming. You can see this was these other memristors which are not part of the sneak path, like M1C, M2B, and M3A, were programmed to a high resistance state, and all these 5 were programmed to a low resistance state. And that is why this sneak path could be formed. It's a simple voltage divider circuit if you look at it, right, from a circuit point of view. So you can predict the current from each of these memristors and also calculate how the path is being created, right? But if for the same IO switch vector, you can see a different 5 memristor long sneak path can also be formed when you just change the programming, right? When you program the other memristors M1B, M2A, and M3C to high resistance state, we can get this second sneak path, which is of 5 memristors. Now you can see with both of these 5 memristor long sneak path, you can get 100% fault coverage, right? Because all the memristors, all the 9 memristors in your 3 by 3 array, they are getting tested with just 2 sneak paths. So with just one vector and different programming, you got 100% fault coverage. So you can imagine how you can shorten the test time, right? Because 5 memristors are getting tested for a fault in this one execution, and the other 5, there will be overlap, right, of one. So other 5 are also going to get tested in the second execution. So you can achieve a very high fault coverage with reduced test time and test cost. So that is our goal of a good efficient test. So what are the advantages we learned? You can see your read test time is improved because multiple memristors are being tested, right, at a time using the sneak path based testing approach. If you would have done a exhaustive testing like marching, like testing one memristor element at a time, that would have been very exhaustive, right? You don't want to do that. It will increase your test time and test cost. So the goal of any test is to provide an efficient testing methodology. And in this case, we looked at stuck at, right? Stuck at faults for low resistance and high resistance. So the main thing is to provide improved test time and shorter test vector sets. So for future research, I mean, that is what is the main challenge the companies are facing, right? You want a reliable test. You are going to have more and more complex designs. You will have a lot of architecture and design issues, right? Because power issues, you will have very high currents. Your size is not going to be 3 by 3. It's going to be very huge, 256 by 256 or even 1000 by 1000. So you will have huge complex designs, and that's when you have to have a good high quality test strategy to get good coverage as well as good test time at the same time. So that is the key takeaway that I would like to tell you folks today, right? The product success, it depends on how you do your manufacturing. Just simply designing the product is not going to be enough. The product has to work, right, at the customer level. We have to ship those products. We have to make sure they work in our day-to-day lives, in our mobile phones, in our hospitals, industries, military, defense, everywhere they are having applications, in your cars. So if you don't do a good test, the product can fail, right? And that can be catastrophic. So product success is dependent on this manufacturing testing. And efficient product testing is very important because test time is expensive, your test coverage and test costs are important. So we saw on an emerging technology like memristors how we can apply all these fundamentals for fault detection. So our main goal is to reduce the test time, improve the test coverage, and the main thing is to have shorter test vector sets on these expensive ATEs. So our design fundamentals that we have for VLSI design are timeless, right? You can see how these test principles you can apply to any technology. Like it was being used on semiconductors, now we are doing on memristors. There will be a lot of new technologies coming up in our future. But these same test principles is what we can keep applying so that we can have an efficient test. So that concludes today's presentation. So few things just for students I thought of sharing. I thought you might be interested, right? What type of skill set really this type of test work might need. So I just put together a list to, to show you what type of test courses you may need or something that you're already doing, right? Like in our bachelor's, we have VLSI electives, we have CMOS, integrated circuit basic principles, we do logic design in our digital design class. But say you go for a master's program, you can even learn more about these design for test architectures, fault tolerance concepts, or we can even introduce these concepts at the bachelor study itself, right? And from industry, you can actually work hands on these tester units, and that is that experience which we don't get, right, in our university or even during masters. I never got that experience to work on a tester. Only when you go to a semiconductor industry, you will actually work hands on that silicon device, or you will get to test it or observe how different type of silicon defects can happen or how to debug them. So that manufacturing testing experience you can get that when you work in these different semiconductor labs. So there will be different challenges at every point of time, right? Like the design complexities, there will be different memory, logic coverages are going to increase, and there is this huge pressure to deliver, right? All these product life cycles are very short, just 6 months when you fabricate the silicon and you actually deliver it to customer. So fabrication to market cycle is just 6 months, right? So in this 6 months, you have to do everything. You have to test the part, you have to make it fault free, you need a good architecture. So yeah, there will be challenges on those fronts as well. You need good collaboration with design teams, design for test teams, technology teams, as well as you have to keep debugging, right? On this silicon for any complex failures that you might observe. So these are some of the challenges right now that all the semiconductor industry is facing, and we are eventually evolving it by coming up with good architectures and good testing strategies. Okay.
Uh, One question, Rasika. Uh, when when you find some fault, what
Mhm.
what will be the next? Do you correct it or what? It is rejected.
So yeah, when you find the fault, yeah, so say you find something right in the metal line, or say something is broken. So we call it a process or a fabrication defect, which we have to feed it back to our fab teams, and they have to correct it in their next metal layer cycle. Because once the chip is already manufactured and faulty, there is no way to fix it unless it's like a cosmetic issue, right? Something like a soft defect, like in the design side, or something we can fix on through our test pattern. But if it's the actual hard defect coming from hardware, then we have to feed it back to the foundry, and they have to fix that in their metal layers, and the next batch of wafers or the package material will have that fix.
But the thing is, see, after the production, the a lot of chips are coming out. Okay, so if one chip fault occurs, then the whole batch you are rejecting, or only that particular part?
No, just that particular part. If one out of say 50 units is failing, we just reject that one part. So there are yield metrics that we are having to determine the pass or fail. Like we study, right, how many are good bins, how many are repairable. Sometimes you're also able to repair the defect. Like for example, if it's a memory defect, right, and we have something failing in the memory column, but say you have a spare redundant column, we can use that to replace the failing column. So such things are also possible, like it's part of fault tolerance or repair circuitry schemes where you can actually recover the part or fix in that case. But yeah, it depends on if your logic has a redundancy scheme in that case. But yeah, if the we don't need to reject the entire batch. Like if the defect is at a specific node, or certain only certain dyes are impacted on a wafer, we screen out those dye, and those dye are sent to the process fabs for further fa, or like failure analysis is what we do on those failing parts.
So guarantee, what guarantee you have, the company gives, not for sure, but internal gives for the any chip.
Right. So, like very mature processes, right? Like right now, we are what, at 10 nanometer and 14 nanometer. These processes are very mature. The expectation is the yield should be at least 90%. That is the commitment from fab. So, when we start off, like when we take the chip, do power on for the first time, right? You will have always have some new learnings, right? Because the silicon bring up is for the first time. But for a mature process like 10 nanometer, 14 nanometer, the expectation is like you'll already have a good yield range. But as you go lower, like 5 nanometer, 3 nanometer, your defects are going to increase. And that's when the challenge is becoming right now, because you cannot, you don't have the visibility into the failure modes that are happening. And that's why fab cannot give commitment for those nodes, and that's why you need good test strategies for that type of material. But I think for 10 nanometer right now in industry, we are doing pretty well. We are at 90% and above yield for different applications. And TSMC, like good fabrication foundries like TSMC, Samsung, Intel, they give that commitment for their silicon. So yeah, it's just the challenges we are facing now is for the lower technology nodes as we are trying to go for lower feature sizes, right? Like if eventually we want 3 nanometer and 1 nanometer, that's where the fab is not meeting success there.
So that there the challenge is there.
Yes, that's where the correct, and that's where we need good test architectures, good testing methodology to catch that defect, because the defect modes are also going to be new, right, on those processes. And also, your equipment will be a bit different, right? You cannot reuse every equipment. Equipment also gets expensive. All these like clean rooms that we have, these different robotic machines that we have for socketing parts. So yeah, that's the correct. I would say the real challenges that we are facing now. Like you can see, the size of the chip is not decreasing, as it's not following that Moore's law trend. Like we were 45 nanometers and now we are stuck at 3 nanometers for so many years. For last couple of years, you are still at 3 nanometers because our yield targets are not being able to meet because of these testing challenges. So that's why we need to really focus on getting a good test. Like it will go hand in hand with design as well, right? Because you need a good design architecture as well along with test. Yeah.
Hello, ma'am. Am I audible?
Yes, yes, yeah.
Hello, ma'am. I want to ask you something. Like during design phase, this as the size of the chip is getting smaller to 3 and 4 nanometer, there's
Mhm.
this process in quantum mechanics called quantum tunneling. So, how does the design team deal with it? Like, if the data is getting lost, even without powering on, then how do you deal with that?
Data, so they will run, so at the design step, you will have visibility only at the simulation level, right? You will have, you'll be able to apply data patterns and see if the design is expected, like whatever is the expectation from this quantum design application that like you said. So at the simulation level, yes, you are able to trace and know, like if there is a issue with my net list, or my net is broken, or some component of my design is not working. So this type of simulation issues you can catch, or like timing issues or anything you can catch easily at the design level. So the issue at the manufacturing level cannot be caught at design, because that is something that happens during fabrication itself, right? But yeah, at design level, through our simulations, we have a pretty good simulation model now, right? We do different temperature sensitive sims, or we also try different skew process corners. Like we try it on a slow silicon, fast silicon. We can model those silicon and try to do it. But certain defect modes, you cannot catch them during silicon. That's when you have to actually wait for the silicon to arrive and then test.
Thank you, ma'am.
Yeah. Any other questions from anyone?
I guess all the doubts were clear. So let's move to our conclusion. This session gave us valuable insights into VLSI's test strategies for Memristor-based circuit and the importance of testing in modern semiconductor technology. Rasika ma'am's industrial experience and knowledge helped us better understanding real-world challenges in the field. We sincerely thank Dr. Rasika Joshi for sharing her experience and inspiring us with her journey and insights. Thank you, ma'am.
Yeah, thank you so much. Thank you, everyone. And thank you, Maitri ma'am.
There will be feedback link in the chat box. Everyone
Uh,
may.
act- Actually, Rasika, fantastic session. It was fantastic, really fantastic. Because you have introduced. Now, this is a informally. I am talking with you because formally, vote of thanks has been given. But the personally, I feel it's a fantastic because you have introduced the how the VLSI VLSI, rather the chip are tested. And the one important thing that Memristor that you have introduced and you have explained it very nicely, very nicely. And it really, in actual, in how the we know the chips, but how the chips are tested, and when it comes to at our end or at the customer end, what is the journey? You have explained it very, very, very nicely, very nicely. Really
Thank you.
great.
I mean, that was my main intention. I want students to, get more into this field. Like when I was a student, I was very excited about VLSI, but VLSI test is such a new and emerging area. Like this is something I understood after I got into the industry. But if we can introduce this early on during our, BTech or MTech degrees, it will be of great help to every student, and they would get interested in this area, and also they might want to contribute more, right, to this field. So
Yeah,
this field has a lot of scope in near
yeah.
future.
One request uh, to get into this field,
Hmm.
irrespective of any background. Yeah, that might be any branch. What the student should learn uh, from your perspective.
Yeah, so like there are some basic course fundamentals like I shared right in the slide. Maybe I can flash it one more time. But VLSI design fundamentals, if you have conquered half of it, right? You know how CMOS works, how this PMOS and MOS, how the logic gates and integrated circuits are created. Test is another layer to it, right? If you already are good with design, if you know your VLSI design in and out, it's just a matter of adding these different test strategies to this another layer. So let me maybe quickly just show you. So yeah, we need like I think that coursework, I think some of it gets introduced during bachelor's or MTech degree also, right? MS programs. So we would be able to see that during our coursework, like this VLSI test principles. Are you able to see my slides?
Yeah,
Yeah. So logic design is one important area. Like we need to have a good understanding of AND gates, NAND gates. Yeah, that is going to come as part of your VLSI design too, right? But these tolerance concepts or testing methodology is something that I learned during my master's degree. But anybody should be able to learn it. Like there are VLSI or design for test courses also on Udemy or Coursera. I have seen them. Like I've seen people who have not done this coursework, but if they are not doing MS degree and still want to learn, you can still do courses on Coursera or Udemy. Just the testing experience on actual hands-on, you will get that in the semiconductor industry. So yeah, if you're really interested in this field, and you should apply for the careers at Intel, Altera, all these semiconductor, there are a lot of growing companies in this area that will give you real hands-on experience on actual silicon, right? Like theory we can learn from our coursework, or we can do simulations on these VLSI circuits, right? That will also give us good exposure to how the data travels or how we can do test. But I would say working in a semiconductor industry, like even a small um, like internship experience, or a full-time experience can give you that insights on how the tester works or how the semiconductor manufacturing is done. But I feel, yeah, these coursework are a good start for any engineer or anybody to get into this field. I have myself, I transitioned, right? I did a lot of control and instrumentation. I loved biomedical. I did a lot of that. But when I got into my master's, I took this coursework a lot, like design for test, fault tolerance, and I started enjoying it. And I got into this area. So it's not like I knew this from the start and I knew what I wanted to do. It's something I discovered along the way. And now, if we introduce it early on to students, maybe if you like this area, you can start exploring it even now and start looking into how you can study these courses, how you can get that industrial experience. And I'm sure anybody can do it. Yeah.
Yes, yes. Okay. So basically, your interest and to go into that field, that's the in your interest and your efforts. These two things are important. Right?
Yeah. Yeah.
Yes.
Yes.
Okay. Yes. Uh, Again, really, really thanks a lot for this such a wonderful session to get actually into the VLSI. So your session has had a journey from start to end, manufacture, not manufacturing process, but you have touched it and the testing process. Okay. So really wonderful session, Rasika, and thanks a lot. Thanks a lot from all the participants, or from the all the faculty members, those who are there in the meet. There are faculty members, there are students, both are there in this meet. So from them, I really thank Rasika for this session, for accepting our invitation. Even though it's US time, still you make it for hours. So really thankful for that. Yeah.
Yeah. Thank you once again, ma'am, and thank you,
Yes.
students and faculty. I really enjoyed today's session. I had a great time. And if you have any questions, I can give you my email ID. You can reach out to me. If you're really interested, I can send you some links and papers. We can definitely talk. So, yeah, just you can send me a note if you're really interested. We can communicate more.
Yeah. You are putting your email ID, or
Yeah, I can share with you, ma'am.
yeah. Yeah,
I can.
definitely share with me. So anyone wants to connect, so with my reference, I will connect with you. So it will be easier for you to
Oh,
guide them. Okay.
sure. Yeah,
Yeah.
sounds good.
Okay. Yes.
Okay.
Okay. Thank you. Thank you so
Thank
much.
you,
Thank you
ma'am.
so much, Rasika.
Thank you. Bye.
Bye bye. Bye bye.
A small request to all attendees: please fill the feedback form, which will mark your attendance.
Yes, Yashasri, do you have any question? Okay. Hopefully, all of you have filled the form. If
Where is the
yes,
attendance form?
yes,
Where is attendance form?
yeah, the Google that link is shared in the chat box, ma'am.
Okay, okay, thank you. Okay, thank you.
Yes. Yes, hopefully everybody has filled the form. Now I am closing down the